Okay, now you can hide everything.
I won't be able to detach.
That's okay. We're winging it. Okay. Okay. So by popular demand, I'm going to finish the disjoint sets part of the lecture, and then we will talk about asymptotics some more. Okay. So to quickly recap what happened last time, we told you about the disjoint sets data structure, and we said the disjoint sets data structure, the users want to be able to connect items, and they also want to be able to check if items are connected. Those are the two operations that the user cares about, and they do not care how we implement it. So then we talked about how we, as the monks behind the scenes, how do we implement the disjoint sets data structure so that the user sees the connect and is connected operations working as intended. So the first thing we tried was, let's have a list of sets, and we analyzed the runtime and found out that's pretty slow. So we could keep track of a list of sets and keep track of which set each item is in, but that's very slow. Then we talked about another approach called quick find. In this approach, we had this array, and in the array, the ith element of the array told me which team element I is on. So if I want to know, element 5, which team are you on? I look up element 5 in the array, and it says 9. And I say, OK, element 5, you must be in team number 9. So to check if two things are connected, that's constant time. We talked about that. You look for the two numbers, check if they're the same. And then to connect things, well, that's kind of slow, because now you have to go through and you have to change all the team numbers for potentially a bunch of elements. So that's slow. That's why we called that the quick find approach. But it was another way to implement the same two operations. Then we talked about quick union. This was another way to implement the same two operations. And in the quick union approach, this was the key idea that I think we kind of missed out because the audio cut out, and we're having so much fun with technology. But the key idea behind the union operation, or the quick union approach to disjoint sets, is that instead of writing here the team number, instead of saying 2, you belong to some team number, you're going to say element 2, you belong to element 1. So every item has a parent or another item that it belongs to. And in doing so, we create these kind of hierarchical teams where we say 2, you belong to item 1. How do I know who item 1 belongs to? I look up item 1 in the parents array. It says 0. That tells me 1, your parent must be 0. And 0, who's your parent? Well, it's -1. That indicates that 0 has no parent. It is the boss of this group. OK, then we analyzed the runtime of this one, and we realized that the runtime of this one, it turns out to be kind of slow again. In particular, if my trees look gross like this, then the time it takes to connect two operations, or to connect two things, is slow. And the time it takes to check if two things are connected is also slow. It's linear time. And we talked about this last time. So today, and I guess for the rest of, I don't know, the 15 minutes, we have to solve this problem, which is we don't want trees to grow tall and ugly like this, because that's going to cause connect and is connected to be slow. Remember, if you want to connect things, I have to go find who the boss is. And if my tree is long and spindly like this, I have to climb all the way up the tall tree to find who the boss is. And same thing for is connected. If I want to see if two things are connected, I have to check if they have the same boss. And doing that requires starting at the bottom and climbing all the way up the tree, which could potentially be slow. So how do we solve it? Well, that's where weighted quick union comes in. So these were our approaches so far. Then we talked about weighted quick union. This is a fourth different approach to implementing disjoint sets. So it's still the same disjoint sets API that the users want to see. They just want to be able to connect things, and they don't care how we do it, but we want to make it fast for them. So the fourth way that we decided to implement quick union, or the disjoint sets data structure, was we took our quick union, where we had this tree-like approach where everyone has a parent, and we really stopped and said, if I have two separate teams, look, there's a team with 0, 1, 2, 4, and there's another team with 3 and 5, and I want to combine them and connect them into one big happy team, well, what is the best way to do it? And we decided there are two approaches I could take. Well, right now, the problem is that there are two bosses. And if I want to connect this thing into one big group, there can only be one true boss. So 0 and 3, you cannot both be bosses. So who should be the true boss? And we said we can make 0 the boss and hang 3 under 0. Or we can make 3 the ultimate boss and hang 0 under 3. We decided that making 0 the big boss is better. And by doing so, we learned the trick, which is that anytime you need to combine two teams like this, you should always take the smaller team, and here the smaller team is the one with fewer items. It's the one with 3 as the boss. And you should hang the smaller team underneath the bigger team. Here, this would be hanging 3 underneath 0. So with that one improvement, it turns out that those really long, ugly trees from before are now impossible. And although we didn't really prove it, it turns out that's going to be true. So we showed you this last time. OK. So the only changes that we had to do, it's still the parent array. We're still having every item have its boss. The only difference from before is that now, if you want to connect up two groups, you should always hang the group with fewer items underneath the group with more items. That's the rule. That's what changes quick union to weighted quick union, because you're checking the weight of the two groups before you combine them. OK, we talked about a really quick implementation thing, which is that how do you keep track of the weight, or how do you keep track of how many items are in every team? Well, when you get to the root, you could, instead of saying 0, -1, you belong to nobody, you can say 0. Your corresponding number is -2. The negative means you're the root. You have no boss. You are the boss. And the 2 means that there are 2 people in your team. OK, all kind of review from last time. So this is kind of where I ran out of time. And the thing I wanted to show you is that it turns out that if I use this weighted quick union trick, that is, I always connect the smaller tree underneath the bigger tree, it turns out I will never get that big, ugly, tall tree that I saw that made my life so miserable. And I didn't really prove it, but I would encourage you can go home, you can play with it, you can try building trees that are long and ugly, and it turns out weighted quick union, the extra rule, will forbid you from making trees like that. So the proof sketch that we had was, this is a group with 0 as the only element. It's a team with 1 item, and its height, we'll call it 0. It's not a very tall tree. Then, if I have a second item, it might look like this. And you're like, uh-oh, it's starting to get tall. But it turns out, if I have a third item, let's say I have another item 2, if I take another item with number 2, and I try to connect it into this group, it turns out I will never, ever get the tall, ugly 0, 1, 2 structure. This will not grow taller. Turns out, if I have another item 2, and I connected it, the 2 would be hung under the 0. It would never be hung underneath the 1. It's OK if that doesn't totally make sense. Go home, play with it. You will see that the only way to get a tree that's taller, that is, with more layers to it, is actually to make another copy, now they're the same weight, and combine these two. And when you combine these two, you take, there's 2 bosses. One of the bosses hangs underneath the other. Now your tree is taller. And again, you're like, well, what if I start hanging more things underneath the 3? Or what if I hang more things underneath the 1? You can try it, but it turns out you will never make this tree taller. You'll never give it more layers unless you do this, which is you make another copy of the same tree structure, right, of 3 layers, or height 2, and you union this with this. And if you union these two, there are 2 bosses, 0 and 4. They can't both be the boss. So we're going to hang the 4 underneath the 0 like that, and now our tree is taller. There's an extra layer, so my height has grown to 3. And again, how do I get the tree with height 4? How do I get an extra layer? You might be tempted to say, well, all I have to do is start hanging things underneath the 7 or hang some things underneath the 5. But it turns out the weighted quick union rule will forbid you from doing that. The weighted quick union rule will force you to keep this tree nice and short. And the only way to get this tree even taller and to give it more layers is to actually create another copy of the tree and hang it underneath 0. So again, kind of a sketch. It's OK if you it didn't totally make sense. The important thing is, if you play with this tree, it's really hard to make the tree tall. And it's really hard to replicate that ugly O of n behavior that we saw last time. So what is the runtime of this new thing that I'm showing you? There's a couple ways to get to it. One way to get to it is I like drawing tables. So here I have a table which says, this is the number of items in my weighted quick union. And this was the height of the associated tree structure. So I said, if there's 1 item, well, the height is 0. This thing has no height at all. It's a very short tree. Then to get to height 1, I needed 2 items. How many items did it take to get to height 2 to add an extra layer? Well, then I had to create another copy, union those 2. Now I have 4 items in total. how many items does it take to make this tree taller by one more step? I have to create another copy with 4 items, and then union those, and that gives me total size 8. And then how many items does it take to create another tree that's 1 taller? I need to make another copy, union it, and then I get a tree of extra height, and now I have 16 items. To make this 1 level taller, I would need 32 items. To make it another level taller, I would need 64 items. So I can write this table out and see if I spot a pattern. If I think back to all my favorite math functions, turns out this one is log base 2 of n. So log of 1 is 0, log of 2 is 1, log of 4 is 2, log of 8 is 3, log of 16 is 4. Don't believe me? Go home and check it out. This is logarithmic behavior. Another way to see it, and we'll talk more about this in the binary search trees lecture, which is where I thought I was going to be doing this talk, but I guess not, is, well, you might also notice that every time the number of items doubles, the runtime, or the height of the tree, increases by 1. So if I double from 8 to 16, the height increases by 1. If I double from 16 to 32, the height increases by 1. And we know the runtime and the height are somehow correlated because really tall trees are slow, short trees are fast. So every time I double the size of the disjoint sets object, the runtime gets slower by 1 unit. What's the unit? Doesn't really matter in asymptotics. We don't care about the exact runtime. We care about the growth. So every time you double the size of the disjoint sets object, the runtime goes up by 1. That's also a sign that you're in log n behavior. So if you ever see functions that do this, you double the size and the runtime slows by 1, you know you've got log n, and that's what's happening here. So all of this sketch is to show you that by using weighted quick union, my runtime is actually now theta log n. Look at that. Theta or big O, and we'll talk about the difference probably next week, or maybe today, of log n. And the reason why that's true is because the connect operation, how do you connect things? You need to climb the tree and find the roots and then tie the roots together. How do you do is connected? You climb the tree and you find out if the roots are the same. So both operations require climbing the tree, and we know that the tree height is log n. That also means the runtime, the time it takes to climb the tree, grows with the function log n, where n is the number of items in the weighted quick union object. OK, that's wonderful. I went from all these slow implementations to a new fancy implementation that's faster. Questions, thoughts? I'm killing so much of Justin's time. OK, so. Oh, you'll take some of mine back? OK, thanks. So one quick note I will mention is you might be tempted to say, all of this makes sense, but why did you always link the shorter, or the tree with fewer items below the tree with more items? That is, when I wanted to compare these two trees, why did I compare that this one had 2 items and this one had 4? Why didn't I compare the heights? Why didn't I say this one is short, this one is tall? Why did I compare the number of items? And it turns out, if you want to compare the height, you can. You could say, you know what? This one's got 2 items, or this one's got a height of 2, I guess, maybe 1. This one's got a height of 2. So this one's the taller tree, so I'll hang the shorter one underneath the taller one. If you want to do that, you can. You end up getting the same asymptotic behavior. You can do the analysis. It's still log n, but it turns out to just be a little bit harder to code. So it turns out we will just use weight, that is the number of items, in each object or in each team, and it works totally fine. You get the same logarithmic behavior. Maybe in some cases one is slightly faster than the other, but in terms of order of growth, in terms of how much slower this gets as n blows up, it's basically the same. So you could use heighted quick union. You could invent your own heighted quick union, and it would work fine too, but we chose to use weight just because it makes things a little bit easier to write in code, which is nice. OK. So that's there in case you're wondering why we didn't do heighted quick union. That's why when we compared 2 teams, we compare the number of items in the team and not the height of their trees. OK. Here's another slide showing you weight instead of heights. They're the same. You could do heighted. You would get log n performance. But we used weight just because the code is simpler. OK, here comes your final shiny topic that you need for the lab 5, and then we're all done. So I will not run through all the math here, but basically this example shows you that by having a good disjoint sets implementation, by switching from this ugly, slow list of sets to this beautiful, fast weighted quick union, your runtime if I plugged in some numbers, it went from 30 years to perform some set of operations to 6 seconds. So it makes a really big difference. By using a good implementation, you've actually unlocked problems that otherwise would be unsolvable. If we were stuck with list of sets, we would not be able to solve this problem with these numbers of operations because it would take 30 years. But if I use my really fast weighted quick union, it takes only 6 seconds. Turns out, for basically all practical purposes, weighted quick union is good enough. You will not notice any sort of slowdown. This can solve gigantic problems very quickly. But there's a question kind of in the back of your mind, like, but can we do better? Like, login was good, but what if we could do even better? So now we're going to dive a little bit into CS theory. We're kind of getting into the point where, for all practical purposes, this is good enough. But we want to find the truly best weighted quick union. So we want to like go to the monk on the top of the mountain and ask, what is truly the best disjoint sets implementation, even if this one is basically good enough for all intents and purposes. So let's go seeking the true greatest disjoint sets implementation ever. Okay. So the key idea to go from good enough for all practical purposes to the theoretical greatest of all time weighted quick union object is, let's say I want to check if 15 and 10 are connected. How do I check if 15 and 10 are connected? I go to 15, I climb the tree, and I say, 15, whose team are you part of? I climb, I climb, I climb, I climb. Ah, your boss is 0. Okay. And remember, the way to do this is to look in my parents array to see who everyone's parent is. How do I know who's 10, who is the boss of 10? I go into parents array 10, your parent is 3. 3, your parent is 0. 0, you're the boss. So I climb the tree, and I find out that both of these 15 and 10 items, they have 0 as the boss. Since both of them have 0 as the boss, well, that tells me they're part of the same team. So I know that isConnected returns true. But as I did this, didn't I kind of learn something? Which is, well, it's true, I learned that 15 belongs to team 0. I also learned that 10 belongs to team 0. But didn't I learn a little bit extra that I could maybe write down and use? Because I learned that, yes, 15 belongs to 0. But then, when I went to 11, didn't I also notice, hey, 11, you must also belong to team 0 because I saw you on the way climbing to 0. And 5, you must also belong to 0 because I saw you on the way climbing. And same with 1, and same with 3. So the clever idea that's going to take us to the next dimension of really fast disjoint sets implementations is, as you climb the tree, you should really keep track of all the things that you see along the way. So as I go, I notice that 11, 5, and 1 are all part of team 0, and so is 3. So instead of having this tree structure, as I run this isConnected operation, I can actually flatten the tree. That is, instead of having 11 tied to some other object, I can just tie 11 directly to 0. Because in the process of checking 15 and 10, I learned that 11 belongs to team 0. I learned that 5 belongs to team 0. Same with 1. Same with 3. So any item that I encounter along the way, I will tie it to the root. And if I do that, and I shuffle the nodes around a bit to make it look nicer, I get this flatter tree. That's kind of cool. It means every time you climb the tree, you're actually flattening the tree as well, because you're seeing items along the way to the root, and instead of leaving them as is, you are tying them directly to the root. So 11's parent used to be 5. And to find the root of 11, you had to climb, climb, climb. But since you already did the climbing, there's no point doing it again later. So I'm going to tie 11 directly to 0, because I learned it's part of team 0. There's no point doing the climbing a second time. So I will just tie it to 0 and get this flatter tree. So if I do this every time I climb the tree, I get this idea called path compression. Every time you climb the tree, anything that you see along the way to the root, you should tie it directly to the root to save yourself some time later. Kind of cool. So don't know if I'll have time for this. I should be a little bit nice to you and give you some time left. So if I want to check if 14 and 13 are connected, what would I do? Well, I'd have to check 14. Who's the boss? Well, 14's parent is 8, 2, 0. But along the way, I learned something. I learned that 8 is part of team 0 and 2 is part of team 0. So I should hook those up directly to 0 instead of leaving them in this tall tree form. And then 13. Who's your boss? 13, climb, climb, climb. And as I climb, everything I see along the way, I should tie directly to 0. because that's what I learned from doing the climbing. So 14 and 13, are they connected? Yes, they are. The climbing told me that. But as I climbed, I also tied all of these items directly to 0, which is kind of cool. This way, if I have to climb later, I don't have to redo the climbing. I already learned they belong to 0, so might as well write that out. So that's kind of cool. It turns out the more you use the data structure, the faster it gets. That's kind of mind-blowing. So this is a data structure where the more you use it, the more you climb the tree and call is connected and call connected, the more you climb and use this data structure, the faster it gets, because the tree keeps flattening because you keep remembering all this stuff about who the boss is. And you keep tying things directly to the root. And if you use this data structure enough, eventually your tree will completely flatten out, which is kind of cool. OK, so it turns out with this path compression idea, even trees like this are just impossible. If I were to build this tree using path compression, it would not be possible. Some of the path would have been compressed. Some of these would have been tied to 0 earlier. That didn't make sense. It's OK. Go home, play with it. But the idea is that with path compression, my trees are now going to be really, really, really flat. How flat is really, really, really flat? Well, we're not going to do the math analysis here. There's a cool paper if you want to check it out. But this tree is so flat that in order to take this disjoint sets implementation and create a tree of height 5, and here this is height 3. If I want a tree of height, or height 2, sorry. If I want a tree of height 5, which is not terribly tall, the number of items you need to create a tree of height 5 is this monstrosity. 2 to the 2 to the 2 to the 2 to the 2, 65,000 times. This number is so big, I think our brains would like collapse into a black hole if we thought about it. There's no way we're ever going to get to this number. So this is it's beautiful. This is the state-of-the-art disjoint sets implementation. It's what you'll build in lab. So what we added at the very end was this path compression idea. And what happened was every time you climb the tree, you should, maybe you remember the term memoize from CS61A. If not, it's OK. But the idea is every time you climb the tree, you're going to take all the items that you see and set their parent directly to the root. That is, you flatten the tree every time you climb it. And by flattening the tree every time you climb it, you end up getting the asymptotic behavior of the inverse Ackermann function, which we won't even talk about. But this function is so slow growing that for any size disjoint sets data structure that you can think of, up to this horrific number, the height of the tree, the runtime will always be less than 5, which is good enough for all intents and purposes. This is state of the art. It's beautiful. We're done. Questions? Question?
So, in the example that you need that little larger number of items to get
Oops.
height of 5, but how many times do we have to call is connected? What class?
The question was, how many times do I have to call is connected to get to a height of 5? That's a good question. I think the idea is, do you want to answer this?
Yeah. So.
I don't understand inverse Ackermanns. OK, here, I'll switch it to Justin. He can answer the question, and then switch it to the asymptotics lecture.
Yeah.
Okay.
No, the mic. The mic's about to die. Let me get batteries.
That means I get to
Wait.
solve?
You get batteries. I'll type it.
OK, you answer the question. I'll get batteries. OK, teamwork. Okay.
So the inverse Ackermann. Inverse Ackermann runtime. However, each time you run one of these calls, you end up reducing the runtime of the next one overall. It's also important to note that this inverse Ackermann is actually on average. So theoretically, with this, you can get a worse time runtime of log n. But on average, you'll get at most inverse Ackermann of n over a sequence of is-connected calls and find calls. Yeah. Yeah, and when we say this is slow growing, this is really, really slow growing. Inverse Ackermann of 3 is, I think, 61. Inverse Ackermann of 4 is more than a Google Plex Plex. And then inverse Ackermann of 5 is a Google Plex 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 Plex. Repeated a Google Plex 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 Plex. Repeated a Google Plex 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 times. The number of times you do that is on the order of a Google Plex Plex times. So it is extremely massive. All right. Anyway, great. I guess that's it for lecture 14.
Yes, sir.
All right.
Okay.
Let me switch over to lecture 15. We've used up 25 minutes. You said this is 15.
I told you it in person.
All right. So fortunately, this lecture does have a bit of way to split it up. Kind of the way that this lecture will go is that we'll go over a few examples of how you might compute some asymptotics, some various runtimes. So before you get that, here's kind of like some basic definitions of these theta classes. They aren't formal definitions, they're kind of just senses of what happened. So theta 1, if you increase the size of your input, it doesn't affect your runtime. Theta 1 just means that no matter how big your input gets, it's the same size. Theta log n, every time you double the value of n, you generally add 1 to the runtime. If you add 1 to n, then it really doesn't affect the runtime too much. Now, I say here that this is base independent. That actually is because regardless of what base you use, whether it's a base 2 logarithm or a base 10 logarithm or a base e logarithm, they're all differing by constant factor. If you know your log rules, log base 2 of n is the same as log n divided by log 2, and log 2 is just a constant. So regardless of what base you have, it's basically the same logarithm class. We just kind of treat it as the same class as a result. We don't say the base. Theta n, if you double the size of n, you double the runtime. You add 1 to n, you add 1 to the runtime. Theta of n squared means if you double n, then you quadruple the runtime. If you add 1 to n, then you're adding about n to the runtime. If you have theta 2 to the n, then that indicates that doubling n will square the runtime, whereas adding 1 will approximately double the runtime. This is actually dependent on the base. Theta 2 to the n is a different complexity class than theta 3 to the n, which is a different class than theta 1.618 to the n, which is a different class from every other base. Any questions before we move on? All right. So let's kind of take a closer look at this example that we had. I think this was Wednesday, was it? I think it was Wednesday.
I don't have any notion of dates anymore.
You don't have notions of dates anymore. All right, let's say it's Wednesday. Anyway, so we tried computing exactly how much runtime this takes. And the way we kind of did this was we first simplified this out. We kind of removed this internal thing here with the number 1, because that's doing just some constant amount of work. And then we kind of added up how many times we did this. For each of these I values, in each of these j values, some of these correspond to 1 unit of work. And if we draw these out in this table, then we get this triangle whose width is 1 and whose height is, whose width is n and whose height is n. And if you remember your area rules, width times height divided by 2, so that's the area of this triangle. So the area is total n squared. So let me give you a slightly different problem here. What would be the runtime for this problem? So now, instead of going through this loop, where it's going from 1, 2, 3, 4 for I, we now double the size of I at every stage. And the j values, we're going to increment by 1 up to I. So how much runtime does this program have? Normally, I'd give like 5 minutes. Let's give... Oh, I'm already in Zoom here, too. I should not be on Zoom here. Let's give until 1:40 for this.
I can monitor it.
All right. That's fine. All right. All right, let's bring everyone back. So, all right, show of hands, who said A, that this is a theta 1 runtime? Who here said B, theta log n? C, theta n? D, n log n? And E, n squared? Anyone say F, other? All right, so it seems like it was about half people said n, half of the people said n log n. Does anyone want to explain their answer? Yeah. All right, so one way we can think about it is that we're doing n computations inside the inner loop, and we have log n total iterations. That's would lead to n log n. I will say that it isn't necessarily that, because we're not doing n things in the middle. If you look carefully, we're actually doing I things inside. And I is not always going to be equal to n. I is most n, but it's going to be less than n for most of these iterations. So it might not necessarily be n log n. I will say that it does provide an upper bound. So we can say that it is O of n log n, not necessarily theta n log n. Did anyone say n? Why? Anyone willing to share why this? Yeah. Yeah. So this is actually kind of how we do it. So let's take a look at how this works, right? So when we say this is 1 unit of work, we're just simplifying this out. And as it turns out, we can even simplify this further and say that this is I units of work for this inner loop. And as we mentioned earlier, I isn't going to always be n. If it was always n, then it would be n log n. But you did say that it's going to be 1, 2, 4, 8, 16. So let's see how this runs. When n is equal to 1, we're going to go through this 1 unit of work. When I is equal to 2, then we'll go through 2 units of work for the second iteration. For n equals 3, it doesn't actually do anything different because the difference between n equals 2 and n equals 3, the inner loop doesn't actually run multiple times. So we need to get to I equals 4 before we actually hit the next block. Here we get 4 units of work at the I equals 4 step. We don't do anything else for 5, 6, or 7 because n is small enough that it doesn't affect anything. Once we hit 8, we run the I equals 8 loop, which does 8 units of work, and so on and so forth. So if we run this, then we have 1 plus 2 plus 4 up to n, where n is a power of 2. So if we tried to graph this, then we're going to get this kind of diagram, which, I don't know, it doesn't look particularly like something. It doesn't look fairly nice. I'm not entirely sure what's going on here. So let's kind of take a look. If we kept going up to these large numbers, then we'll see that it largely increases by these amounts, right? So 4, you get 7, 7, you get 7, 8, you get 15, 27, 31, 715, you get around 1,023. And, you know, if you're trying to look around, play around with some functions, eventually you realize that it always ends up staying between 0.5n and 2 times n. Like here's the value of 0.5n, 357. Here's the value of 2n, 1,430. You always end up staying between these. So if this pattern holds true for every single other value of n, then that means that we do have a theta bound. We have a theta of n bound because we're bounding between 0.5 times n and 2 times n. So this would be nice if this was always true, but I don't exactly... Are you convinced that it's always going to stay within this area? Why not? Well, I don't know. What if this function just keeps going in a weird pattern? I don't know. I'm looking at this, looks kind of like it's staying within, but I'm not sure. If it goes really large, then eventually it might go off. So let's actually prove this exactly. So here's the list of like boxes from 1, 2, 3, 4, 8, 16. And I'm just going to move around these boxes a bit to see if I can make the math a bit easier. So I'm going to move this 1 box down to here so that it kind of fills this spot. I'm going to move this 2 box down here so that it fills this. And I'm going to actually move this over like this. And one thing we'll notice is that at each of these steps, this total box size is less than the size of this bottom box. So 1 plus 2 plus 4, it's less than the 8. 1 plus 2 plus 4 plus 8, it's less than the 16. In fact, it's always exactly 1 less. So if we do 1 plus 2 plus 4 up to plus n, then that actually means that our sum is going to be 2n minus 1. 2n minus 1, if we actually do the theta bound, that's definitely theta of n. So we can say definitively that this sum, 1 plus 2 plus 4 plus 8 up to plus n, is equal to theta of n. Now, this is just kind of a version of this equation. If you do 1 plus 2 plus 4 plus 2 to the k up to 2 to the k, then that's theta of 2 to the k. So 2 times 2 to the k minus 1. We're just kind of replacing 2 to the k with n here. So does anyone have any questions on like how we got this? I know this is kind of fast. But all right. So, all right, everyone say this with me. There is no magic shortcut for asymptotic analysis. No. There is no magic shortcut. Every semester we get some students who are asking, like, is there a general idea when things are theta of n or theta of n log n? There is no magic shortcut. We don't have an easy way of saying whether a function is theta n or theta n log n, except through the direct mathematical analysis. It often requires a lot of careful thought. It's actually provable that it's impossible to find the runtime of every single function. Not even that it's hard. It's literally impossible. There's no program that can do this. There's no humans that can do this. There are functions whose runtime is independent of ZFC, like the mathematical basis entirely. CS70 and 170 actually covers this in a lot more detail. This isn't considered a math class, but we will expect you to know these 4 equations. Namely, if you add up the sequence of natural numbers, 1, 2, 3, 4, 5, 6, 7, up to n, then you get about n squared. As a generalization of that, if you do 1 squared plus 2 squared plus 3 squared plus 4 squared, that adds up to 1 n cubed. If you do 1 to the 3 plus 2 to the 3 plus 3 to the 3, all the way up to n to the 3, that adds up to n to the 4th. Similar to that. And then the other one is the exponentiation rules, which is if you do 1, 2, 4, 8, 16, doubling every time, then it's approximately the theta of the last term. And the same is true regardless of what the base is. So if it's not doubling, if you're tripling, then it's still the same last term. So we also write it in this format. We just write n equals k to the q because we want to use n as our last term. In our code here, we had n be this largest possible value of I, so it made sense for this last term to be bounded by n. That's why we didn't write 2 to the q, where q is equal to log n. That just ends up canceling out, so we just wrote n here. Now, in order to actually determine the runtime of a function, we kind of need to play around with it, divides into pieces. There's generally some strategies. We can find some exact sums. We can write out examples. We can draw these pictures. We had these pictures where I showed you like the area. Here's an example from an actual research paper where what they did was they interpreted the runtime as the volume of this shape. And if you do that, then you end up finding that it's equal to n times n because that's the cross-sectional area of this, and then times m because that's how wide this thing is. Now, I did say there's no magic shortcut. There is this well usually here, and here is actually kind of this magic shortcut. So if you have some function f of n, and f of n is continuous and strictly increasing, then you end up getting this area diagram. Now, for anyone who's taken Math 1B, what does that look like? An integral? Yeah. In fact, it's actually a Riemann sum, not an integral specifically. But an integral is a good approximation for a Riemann sum. In 1B, you use a Riemann sum to approximate an integral. In 61B, we use an integral to approximate a Riemann sum. So if you know your calculus, that is your shortcut. And in fact, this kind of explains why we have these equations in the first place. The integral of x to the n, where n is some constant, is x to the n plus 1. The integral of e to the x is e to the x. Yes? Yes, in a way. Fx is just any generic function. Asymptotic analysis is not directly related to the runtimes of functions. We're just using the runtimes as a way to express like a function of how long something is running. Yeah. So theta bound is specifically a theta bound on the runtime of a function. And the runtime of a function is a mathematical function. We send in an input and we get out a time, right?
So what is f? Like in relation to our program?
F, if we wanted to like use this equation to evaluate the runtime of a function, then f might be, for example, like one component of the runtime. So in the examples that we showed earlier, we kind of split up the runtime into the inner loop of I equals 0, I equals 1, I equals 2, and so on. And for each of those, we determined a runtime, right? And then for each of those, once we added them all up, we get the total runtime of our function. So f can be any sequence. In order for this rule to apply, you need specifically for f to be increasing and continuous. But those two are fairly, most functions do, that you find in this computation do end up fulfilling those properties. So you get this fairly common. It's just we don't expect you to know 1B stuff, so you don't need to calculate integrals here. Yeah, you do not need to do integrals in this class. So yeah, but even with this shortcut, it tends to be somewhat limited in scope. You don't have these functions for every single operation, and even then you need this particular summation for this to work. So it tends to be limited. In fact, if we wanted to go to that disjoint set thing and compute y is this theta of inverse Ackermann of n, I think that was solved in like 2001 or something. Like it was like 30, 40 years after the original algorithm was discovered. So this tends to be really, really hard. Like modern research fields are based around asymptotic analysis. All right, any questions up to here? All right, I think I have time to go through this amortized analysis part. We'll cover the rest tomorrow, I guess, or Friday. So I'm going to play around with this function that we saw earlier. This is theta of n runtime, right? And we said this is theta of n because it's 1 plus 2 plus 4 plus 8 up plus n, and that equals theta of n. So I'm going to play around with this, and let's see what happens. I'm going to add theta of n work here. The total runtime, it's still theta of n. I haven't changed the theta bound just by adding this for loop that does n units of work. All right. Now I'm going to combine these for loops. This isn't going to change the asymptotic runtime because I haven't really changed what gets done. The total amount of work is still the same. I'm going to actually put these into separate functions. Function calls, they actually just take a constant amount of time. I can treat this also as 1 unit of work. So this hasn't changed any of these runtimes. This is still theta of n, total runtime. And you know what? I'm going to rename some words all over the place. Does this look like anything we've seen before? What does this look like? Yeah, your array list. Remember when we said that increasing the size multiplicatively ends up yielding approximately constant time? Well, this is kind of why. If you add n items to an array list, then according to this analysis, this code, if you run it for n units of time, that's the same as this original print party thing, which we just said was theta n time. So adding n items takes theta of n time. If we divide those two out, that means that adding one thing takes, on average, 1 unit of time. This is known as amortized runtime. After you do n add last, the runtime of this version, where you multiply things, is theta of n. Now, you can do some similar analysis with this one where you add a factor, and you'll find that this actually ends up being a runtime of theta of n squared. After n add last, you get theta of n squared runtime, which means that after each add last, for every add last, you get on average n runtime. So even though these worst case resizes are still theta of n, if we look at the average runtime, we can see that this add last, where we do multiplicative resizing, is asymptotically much better than the version where we add only a constant amount to each item. So this is kind of why we end up using this multiplicative factor, because this asymptotic runtime is so much better. Now, this isn't worst case runtime, because the worst case is still theta of n. Every time you resize, you need to spend that really long time copying and pasting those values. But we can call this amortized runtime. And this amortized runtime is actually sometimes more useful than worst case runtime, because any single operation may take longer. But if we use this over a large number of operations, we are going to have a better average performance guaranteed. No matter how we add or remove items, after n operations, we will have theta of n total runtime. So after n operations, we will have on average theta of 1 runtime. So disjoint sets also had this idea. As I mentioned, theta of log n was the worst case, but inverse Ackermann of n is the amortized runtime. So we will sometimes compute the amortized runtime instead of the worst case runtime. All right. Any questions? All right, I have 2 minutes. Do I have time to do this? I don't think I do.
You want to give them like a flavor of it and finish next time?
Yeah, let's do kind of a flavor. All right. What if we had this function? What's the runtime of this function? Try doing, let's actually just talk for the next 2 minutes, discuss with your neighbors, and we'll do like a poll at the very end to see what everyone thinks. How's chat going?
Someone wants to know why time. Any more time. Brains are right.
What's the question?
Why is it amortized?
Why is it amortized constant? Yeah. So I think someone on Zoom asked why the earlier function was amortized constant. Well, the reason why is because if we have n things and we take a total of n time to finish those n things, then on average, each thing took 1 unit of time. So amortized is just another way of saying on average. So if you have n things that take a total of n time, then on average, each thing took 1 unit of time. All right, let's bring everyone back. So before we go, who here said this is constant time? 1 person, 2 people, 3 people. Who here said it was log n time? Who here said it was n time? Who here said it was n squared? Who here said it was 2 to the n? Everyone. Why is this 2 to the n? Yeah, every single time you go down, it doubles in size. Yeah. So when we start on Friday, we'll go over exactly the formal understanding of why this is 2 to the n. But it seems like a lot of people are thinking it looks like a 2 to the n is function. That's great. All right. We'll continue this on Friday. See ya.